In this video, we're going to talk about variability and standard deviation. So some of the concepts that you have to keep in your mind are mean, median, mode, and any of the statistical notations that we've already introduced. Mostly how to find mean, but there's a couple other mathematical equations you also need to keep about you, just the order of operations and what comes first, what do you need to complete first in any kind of mathematical equation. Okay, so just a quick review on some of the symbols that we have learned. So take a couple seconds and push still pause on the video, and you can come back and I will fill in the answers for you. Okay, excellent. Hopefully you were able to work through that, and these are some of the answers. So X is B, so X is going to denote anytime that we're using a raw score, so one individual person's score, also called datum, right? Okay, N is the population number of scores, so it's N, big N. Number 3, mu, and that's kind of looks like an upside down N or a really fancy U, right? This is the population mean, and it's pronounced mu, mu. Okay. And little n is when we're trying to make a notation for a sample of scores. So, and big N for population and little n for sample. This little squiggly e, right, that's the sum or summation notation. So that's the sum of all the raw scores, and we're going to use that a lot in this chapter. And then M, big M, is the sample mean. So again, mu is population mean, and M, big M, is sample mean. Okay. So today we're going to talk about variability and standard deviation. Now, standard deviation really is what we're trying to get to, but variability is also very important. It shows how much the scores are going to either, be tightly clustered around one another, or if the scores in your study, vary or spread out, right? So if I give the first quiz and all of you score in the 80s, right? Some score like an 81 or an 87, an 85, an 89, but nobody scores in the 20s or 30s or 90s, right? That would be that your variability is very low, which is good. If though on the first quiz, then some people scored in the 10 or in the teens and in the 40s, we had one person get 100%, right? Variability is all over the place, right? So your scores be more spread out and variability be very high. Why we find variability, or what that measure is trying to help us with, is just trying to help us again describe that distribution. And once we know that, we can then tell how representative one individual score is on the entire distribution. So we have 3 ways we can measure variability: range, standard deviation, and variance. Let's start with range first. The range is the distance covered by the scores in the entire distribution of scores, right? So you're going to go from the smallest score, the smallest value, all the way up into the highest value. I know we talked about upper real limit and lower real limit before, so keep that in mind when you think about range, because you want to find whatever the highest score is, so your upper real limit minus your lower real limit. That's going to give you your range. So range really is only based on 2 scores, not all the individual data or numbers collected. And because it's only based on 2 scores, it's considered a crude or unreliable, or not that good of measure of variability. If my dean asked me, how did the students do in the last quiz? And I said, oh, they did pretty good. And he says, what was their range? Well, if somebody didn't show up for the quiz and I gave them a 0, right, their range would be really high, like a 90-point spread or something like that. So it's not really reliable on trying to see how well a population or a sample is really doing. So standard deviation and variance, these are the 2 most common and most important measures of variability. So we use range a little bit, but really we rely more on standard deviation and variance. And what this is a measure of the standard or average distance from the mean, right? And it's going to try to help us again describe how the scores are either clustered really, really tight together, or if they're really spread out. And the calculations are going to differ if you're dealing with a population or a sample, but I'll show you an example for both of those, for a population and a sample. Let's take a look at this. You have the one blue line here, so the line right here, right, and it's more spread out. It's like almost looks like someone who's like sitting on the top of it, right? Squished down. The tails are very thick, right? So you have thick tails and not high of a peak, right? So we would say this has, so the mean is 50 and standard deviation of 20, right? So this has a lot of variability. Now look at this red one right here. See how it peaks up really high? What that's saying is that all the scores, or most of the scores, really cluster around this 30, right? With a standard deviation of only 8. Okay, so how do we get standard deviation? Well, step 1, you're going to determine the deviation, and the deviation is just that distance from the mean, right? So each individual score has a distance from the mean, right? So if the average score was 78 and you scored a 92, you would take your 92 and you would minus the 78, and that would be your deviation for the raw score, right? So standard deviation is trying to figure out how well all the scores do that. Okay, so you're going to calculate that mean of deviations, but half is always going to be on the left-hand side, so lower than the mean, and half is going to be on the higher end, or the more than the mean. So that balance is always going to be zeros right there in the middle. Okay. To get rid of this equaling out on both sides, we square it, right? So you get rid of the pluses and the minuses, or the positive and negative numbers, and you're going to square it. Okay, and when you compute that mean square deviation, what you're actually doing is you're finding variance. Okay, so population variance equals the mean squared deviation. And all variance is just the average squared distances from the mean from all those different scores. Okay. All right, step 4. You're going to try to compute the measure of the standard distance of the scores from the mean. And again, variance tries to measure the average square distances from the mean for all those scores, and it's not going to be quite on mark or on goal. Okay, so you have to have a correction, and the way we correct this is we square it. Okay, so standard deviation is just the square root of variance. So when I show you, and I have videos on this too, we're actually calculating for a variance, and then we just take the square root of that and we find standard deviation. All right, take a look at this histogram here. We have the average, right, the population mu is 6, but we have an outlier over there, the 1, right? And so the largest distance between the average, 6, and the score that's the farthest away is 5 points, basically, right? Because you have one person scoring a 1, and you had an average score of 6, and so you have that 5 points. That's the maximum number that you're going to have for standard deviation, because you don't have any scores bigger than that. Now, the minimum distance, or the minimum score, is going to be either 7 or 5. Either one, it's fine. They're both equally far away from 6. So your standard deviation for this example is going to be somewhere between 1 and 5. All right, variance. Variance equals SS divided by N, or sum of squares divided by the number of raw scores that you're dealing with in that study. Okay? There's 2 different ways you can compute sum of squares. Okay, there's actually 2 formulas for sum of squares. There's the definitional formula, and there's the computational formula. So the one on the left there is just in green. It's just the definitional formula, but the one I really want you to focus on is the computational formula. This is one we're actually going to use. So sum of squares equals sum of x squared minus sum of x squared divided by n. And the n can either be n, capital N for population, or n little n for samples, either one. Same formula for both populations and samples. Okay, so again, here is what it looks like for population variance, the formula and notation. So you have variance equals sum of squares divided by n. And then to get standard deviation, all you do is take whatever the variance is, and you take the square root of that. So if I had variance equaling 25, then my standard deviation would be 5. The notation for variance is that lowercase Greek letter. It looks like a really curly O, right? And so that's how you would write that, and you're going to see that in our equations, right? And the standard deviation is the same thing there too, but with a 2 on top, right? Okay, so let's keep on. All right, take a look at this. And in this chart, what you see here is you see a normal distribution, right? We're going to talk about normal distributions a lot. But what this is the IQ score. So the average or the mean IQ score is 100. And as you can see there, the color breakdowns in the dark blue, 68% of us fall plus or minus 1 standard deviation from that average of 100, meaning if our standard deviation is 15, then 68% of us fall between 85 and 115. Now notice how small the tails get on both sides, right? So in the orange there, you have those people who have an IQ between 115 and 130. And then in kind of the medium blue, you'd have the 130 to 145, and the gray, you have those top 0.1 percenters or bottom 0.1 percenters having an IQ score of either lower than 55 or higher than 145. So the question I posed down there, if a person scored 130 for an IQ, how would you describe that? And what you would say is, you'd say, well, they are 2 standard deviations above the mean, right? Because the standard deviation is 15, so 2 times 15 is 130. So if they have an IQ score of 130, they would have an IQ score 2 standard deviations above the mean. And then what about an IQ score of 65? Well, that would be slightly, greater than 2 standard deviations below the mean, right? Okay. And we'll talk about standard distributions and normal curves a lot more in the upcoming chapters. But this is pretty well used in statistics because it breaks up so easily. Numerically, it's easy to look at, right? 100 with a standard deviation of 15. Now, if you were to say out of 100 people, right, then you'd say, well, then 68% of us would have an IQ score between 85 and 115, right? 34% of us would have an IQ score between 100 and 115. And then only 14% of us would have an IQ score from 115 to 130. Well, only 2 of us would have an IQ score of 130. Now, keep in mind that the distribution is symmetrical, meaning whatever happens on the right-hand side also happens on the left-hand side. So just because you say, well, 2 standard deviations, well, the bigger question is above or below the mean? Let's take a look at these two. First question, true, false. The computational and definitional formula for sum of squares sometimes gives us different results. And then if all the scores on a data set are the same, the standard deviation is equal to 1. Okay. So they're both false, actually. The computational formula will give you the exact same answer as the definitional formula. The definitional formula is just easier to use, right? But the results are identical. And when all the scores are the same, they're all equal to the mean, right? So if all the scores in the first test is 87, the mean is 87, they don't deviate at all from the mean. They have a deviation of 0. So some of the goals of inferential statistics is to draw general conclusions about a population, right? So how we do this is we do studies on samples and then infer what we learn from those samples back to the greater population. Right? So samples have less variability than their populations because they could never have more variability. And again, variability just means how much the scores vary or differ from one another. Okay? So you're never going to have a sample that's crazier than the population because you're pulling the sample from the population. Okay, so for a sample, it's going to look a little bit different because we have that sampling error, right? So the sum of squares is the same, right? But now, instead of just the sum of squares over n, or sum of squares divided by n, to find variance, you're going to find variance by doing sum of squares divided by n minus 1. And the square root would then just be taking the square root, the standard deviation would be taking the square root of that variance then again. And n minus 1 is called degrees of freedom, and we'll talk about that a lot more too. So again, we have here, in this example, we're going to use a census, right? We're going to pull 2, 4, 6, 7, 8 people there from that population, and you're going to learn something about them, right? So if you're going to run analysis, you're going to run population variance, you do the sum of squares divided by n, and then standard deviation would just be the square root of that. And then if you're going to do it on a sample, though, you would do sum of squares divided by n minus 1, or sum of squares divided by degrees of freedom. Degrees of freedom, again, being n minus 1. Okay. So with population variance, we know a couple things. We know what the mean is, right? And then we know that we're trying to get the deviations from that known mean, okay? But with a sample, the population mean is unknown. So we can't necessarily say 100% surety this was going to be for all populations because we're just pulling from a sample. So what we do is we say, okay, well, we're going to have degrees of freedom. And degrees of freedom at this point, and it will change depending on what kind of statistical analysis you're running, is n minus 1. Okay, let's take a look here. A sample of 4 scores has a sum of squares of 24. What is the variance? So think back to what's your variance equation? So you know n equals 4 and sum of squares equals 24. All right. Again, variance is sum of squares divided by n minus 1 because it's a sample, not a population. Okay. What about this one? True or false? A sample systematically has less variability than a population. Or, and the standard deviation is the distance from the mean to the farthest point on the distribution curve. So push still pause if you need to, and then come back before I show you the answers. So the first one, right, extreme scores affect variability. This is true, but are less likely to be included in a sample, right? So again, that sample can never have greater variability than a population. And then the second one, the standard deviation extends from the mean approximately halfway to the most extreme score. So that second one would be false. Okay. So let's take a look at a real example here. So we're going to use the freshman 5, right? The myth is that when students go away to college, they gain 5 pounds. We're going to try to find out, is that myth or reality? So we're going to take a look at weight changes in pounds. And so again, you see here, these are your raw scores. You have somebody who gained 5 pounds, somebody who gained 1 pound and 4 pounds and 7 pounds, somebody who lost a pound, all right, so -1, someone who remained constant, they didn't gain or lose any weight, and then the last person there gained 2 pounds, right? So the first thing you want to do is find the sum ofs, right? You want to find the sum of x and the sum of x squared. And again, all sum of means is just added up, right? So you're going to add up 5 and 1 and 4 and 7. You're going to -1, stay neutral at 0, and then add 2. So sum of x equals 18. Then, to find your sum of x squared, you're going to square each one of the x's first and then sum it up, right? So you're going to square 5, which is 25. Square 1 still stays 1. Squares 4 turns to 16, right? You're going to keep doing that all the way down. Now, do take note what happens to the -1. Because it's negative, when you square it, it just becomes, positive. 0 just stays 0, and then 2 is the 4. So we have sum of x squared as 96, because we just added up 25 and 1 and 16, 49 and 1, that kind of stuff, right? So now we have sum of x and we have sum of x squared, which means we can start doing our sum of squares formula. Okay. So we have variance there. We have variance equaling sum of squares divided by degrees of freedom. Let's find our numerator here. All right, so here is our sum of squares, all right? But we don't know our sum of squares yet, but it's our sum of squares formula. So we have to find this first and then plug it into here, and then we can divide by degrees of freedom. Okay, so sum of x squared is 96, right? So we put that, right, so sum of x squared, 96 right here, divided by 18, sorry, minus 18 squared divided by 7. Now keep in mind, this n right here is not the degrees of freedom, even though you're dealing with a sample, so it's just 7. The degrees of freedom is going to come later. Okay? So we have right here, on the numerator, we have 96 divided, or minus 18 squared divided by 7, 49.71. Then we're going to divide by that degrees of freedom, the 6 right here. So we have 49.71 divided by 6. We have 8.29 as our variance. And again, all we have to do now is just take the square root to find standard deviation. So again, standard deviation equals the square root of variance, or sum of squares divided by degrees of freedom. So we have variance of 8.29. We have square root of that is 2.88. But what does that really mean? Again, we knew that the average score, or the average weight gain, was 2.57 because we just added up all the weight gain or losses and divided by 7 because that was our sample size, right? So we know that we have an average score of 2.57, so right about there, right? And then with a standard deviation of 2.8 pounds, meaning at this particular college, we gathered 7 people, and we asked them how much weight did you gain to lose. The average person said it's about 2.5 pounds. Well, there's a standard deviation of 2.878 pounds, meaning if you gained, I don't know, closer to 5 pounds, then you'd be closer to 1 standard deviation above the mean. If you didn't gain any pounds, you'd be closer to 1 standard deviation below the mean. Okay, and this is what it looks like graphically. So again, we have the average here, 2.57, and then we have the standard deviation of 2.8 on this side. And again, because it's symmetrical, 2.8 on the other side. So to be 1 standard deviation above the mean, you would be 5.45 pounds heavier than when you started. To be 1 standard deviation below the mean, you would have lost about 1/3 of a pound. Now these keep going out, right? So I could have another, if I wanted to have 2 standard deviations above the mean, it would be closer to 8.5, right? Okay. So again, the goal of the inferential statistics is to detect meaningful and significant patterns in research results. And the variability or differences found among those scores influences how easy it is to see high patterns. If you have high variability, or if those scores are all over the place, it really obscures patterns. It's hard to see what the pattern is if the scores are just all over the place. But low variability increases that ability to see patterns and trends. Okay. Oh, and sometimes variability is called error variance. So don't get thrown if you see that in a textbook somewhere, error variance. Okay, so please do your homework and then email me or text me with any questions.